Hello, today I will talk about Ohm's law and series parallel circuits. This one is basically for DC circuit analysis but also can be implemented for AC circuit analysis. Topics to be discussed are basically Ohm's law and then series circuit, parallel circuit, and then a combination of series and parallel circuit. And I will give you some examples and I will try to solve some problems. So what is Ohm's law? So think about a resistor right here, R, and what is the current flowing through this resistor? Say it is I, and what is the terminal voltage? Terminal voltage is V. Now, according to Ohm's law, the ratio between voltage and current is always a constant. Okay, so what is meant by that? Say you have a voltage V, so V, and you have that current I, so always V over I is a constant. Given that the temperature of the conductor is unchanged and this constant is basically the resistance, so V over I is equals to R. In other words, we can say V equals to I times R. We can also show it graphically. Say in x-axis we are trying to plot the voltage V, and in y-axis we are trying to plot the current I. Now if the voltage is increased, current will also be increased in a proportionate manner. That means the VI curve will be a straight line like this. Now let's try to see a series circuit. Now how the resistors are connected in series and what will happen in that case. Now let's see. Think about these three resistors, R1, R2 and R3. They are connected in series. So a series connection is basically, this is a resistor, right? So R1, it has two terminals, number terminal 1, terminal 2, and we have another resistor, say terminal 3, terminal 4, R2. Now two elements are connected in series whenever they are kind of in a handshaking mode. That means if we connect these two, then these two are connected in series. Now if we have another resistor right here and they have, so that means two resistors are said to be connected in series whenever they have only one common node, this one. And these two resistors, R2 and R3, if they are connected in series, they should have one common node right here. So in this way, which means this R1 and R2 has only one common node right here, R2 and R3 has another one common node right here, and all R1, R2 and R3 are connected in series. So this is not a series connection right here. So if we think about something different right here, so R1 here, R2 here, right? So they have two common nodes right now. That means they are not in series connection. Now you know what is a series connections of the resistors. So what are the characteristics or assumptions we have to follow for a series connected resistors? If we think about a current is flowing right here, I, so that current is basically going towards all the way right here, right? So through all the resistors and it is coming back here. This one is basically a plus minus 24 volts. Okay. Now same current will flow through all the resistors which are connected in series. Now think about this one. Now if we have a voltage source right here, say this one is V, this one is R1, R2. Now if this is a branch current I, now whenever current is flowing right here I, after coming here it will divide it into two resistors, right? That means the same current is not flowing through all the resistors right here, so this is not a series circuit. Another thing, different resistors, okay, so we already know that Ohm's law, right? So the voltage across this resistor R1 right here is I times R1, that is V1. That means every independent resistors have their independent voltage drops, and these voltage drops are also additive, which means this 24 volts is equals to V1 plus V2 plus V3. We're right here. Applied voltage equals the sum of different voltage drops. Okay, so this voltage is applied voltage, is the sum of this one, and this one. Okay, the resistors connected in series are also additive, which means RT is equals to R1 plus R2 plus R3. Now if we have n number of resistors, so Rn RT equals to then R1 plus R2 plus dot 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 plus Rn. Like this is generic expression whenever resistors are connected in series. Similarly, whenever resistors are connected in series, the powers are also additive. So if we think PT is the total power equals to P1 plus P2 plus dot 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 plus Pn. If we think about only this one, so PT will be then equals to P1 plus, sorry, this one is P1 plus P2 plus P3, okay, which can be, you know, I square R1 plus I square R2 plus I square R3, which is equals to I square times R1 plus R2 plus R3. Okay, now PT is equals to I square RT. So depending on the type of problem, you can find out the value of particular parameters using different equations. Okay, so these are the things you need to remember whenever resistors are connected in series. Now whenever the resistors are connected in series, we can generate a voltage divider rule. So what is a voltage divider rule? That means if you want to find out voltage across a particular resistor, given that the total voltage of the circuit is known, okay, so this one will be basically plus minus, okay, this is a typo. So let's try to find out the voltage divider rule. So we know that total voltage V is equals to, say this one is V equals to 24 volts, V1 plus V2 plus V3, right? So we can say that if the total current is I, so IRT equals to V1 means I1 R1 plus V2 means I2 R2, right, plus V3 equals to I3 R3. Now since we know that same current is shared by all the resistors connected in series, so instead of I1 I2 I3 we can write it I, right? So RT is equals to R1 plus R2 plus R3. We already know that, right? Now let's try to find out what is the voltage V1. Now V1 is equals to I R1. Now we already know that what is I. Okay, so V is equals to I times RT for this entire circuit, right? This voltage is this voltage, okay, and this I is basically this current. Now if we would like to find out V1, we can replace this I. So from here we know that I is equals to V over RT, right? So I is equals to V over RT, so we can say that V over RT times R1, or we can write down V1 is equals to, like in simplified form, R1 by RT times V. So this one is basically V, I'm sorry, this one is basically V. So this one is voltage across the resistor R1. In similar way, you can write down V2 is equals to R2 over RT times V. This is okay. So and V3 is equals to R3 over RT times V. So this is known as voltage divider rule. If you know the total voltage and the total resistance, you can find out voltage across every resistors. Those are connected in series. Now we need to find out a generic expression. So generic expression is Vx. Say this is Vx, or anything like this one, also another Vx, like just a variable. So if you want to find out the voltage across any element, so what you have to do, you have to, okay, you know that RT times V. That means all you have to do, this is a generic expression. If you want to find out voltage across any particular resistor, then multiply that resistance with the total voltage and divide with the total resistance RT, right? So this expression actually we can write down in general in this way. For n number of elements connected in series, the same thing we can also write down in this way: Rn RT times V. So either this one or this one, like all the same, but in whichever way you prefer to remember this, you have to, right? Let's try to solve a problem in terms of Ohm's law. Here, three resistors R1, R2 and R3 are connected in series across a 12-volt battery. So this one is 12 volt. The first resistor has a value of 1 ohm and the second resistor has a voltage drop of 4 volts. Okay, so this voltage is 4 volts and the third resistor has a power dissipation of 12 watt. Okay, now we have to find out the value of the circuit current I. That means I equals to what? Now think about it. This circuit has a voltage drop V1, this resistor has a voltage drop V2 and this one has voltage drop V3. Now total voltage V equals to V1 plus V2 plus V3, right? We also know that V equals to I times total resistance, say RT, okay, which is basically I times R1 plus R2 plus R3. So V equals to this. Now what do we know about V1? So if we think about it, like if we extend it further, we know that V1 is equals to R1, sorry, it's I times R1, and V2 equals to I times R2. Similar way, V3 equals to I times R3, right? So now, so here I times R1, so I, and R1 has a value of 1 ohm, that means it is I. So I times R2 plus I times R3. And these volts V equals to 12 volt. We already know that. So this equals to I plus this IR2 is here V2, right? And this is equals to 4 volts. And so we can make it, replace it with 4. Now excuse me, we left with IR3. What I'm trying to do right now, we have another parameter given. So P3 is equals to I square R3 is equals to 12 watt. We know it just from here, it is given, right? So I'll try to replace this one with something 12 watt, but we have to multiply it with I. So let's multiply I with everything. So I square plus 4I plus I square R3. Now what do we get here? So we'll take I square plus 4I plus this one is again now 12 equals to 12I. So we get I square minus 8I plus 12 equals to 0. Now we get I square minus, if we solve this one, we will get basically, I minus 6, I minus 2 equals to 0. Now we got two values of I. So I equals to 6 ampere, 2 ampere. So these are our two answers. That means the value of the currents could be either 6 ampere or 2 ampere. Now we will try to solve the problems, this problem, like, because this is a given problem where all the resistances are known, 2, 4 and 6 ohms, and the voltage across the series resistors is 24 volts. Voltage divider rule, Vn equals to Rn over Rt times V, right? So what is Rt here? Equals to R1 plus R2 plus R3 equals to 2 plus 4 plus 6 ohm. This makes it 12 ohm, right? So we would like to get the voltage V1 equals to, so R1 over RT times V. So 2 over 12 times 24. So this is V, right? So this makes it 4 volts. Okay. In the similar way, using voltage divider rule, if we want to find out voltage V2 equals to R2 over RT times 24. So R2 is equals to 4 times 12 times 24 equals to 8 volts. V3 equals to, similar way, 6 over 12 times 24, which is equals to 12 volts. Now in order to verify whether your results are good, so you have 12 volts, you have 8 volts, and you have 4 volts, right? You know that V is equals to V1 plus V2 plus V3, right? That means summing of all these voltages in series will give up this 24 volts. Now this is actually 4 plus 8 plus 12, which makes it 24 volts, which is basically this voltage. Now you know your voltages V1, V2 and V3. Okay, now let's move to the parallel resistors. We have already seen that whenever resistors are connected in series, they should have, like, between two resistors, they should have only one common node. But if they share two common nodes, then the resistors are connected in parallel. So think about this resistor R1 and this resistor R2. Now this is their common node and this is their another common node. So this is node 1, this is node 2. Okay, now if two resistors shares like two common nodes, then those two resistors are connected in parallel. Now you have another resistor connected right here. These resistors also shares the same common node N1 and N2. That means this resistor R3 is also connected in parallel with them, right? So which is basically shown right here in this figure here. Now these three resistors, whenever connected in parallel, they have some special characteristics. That means all the resistors connected in parallel will share the same voltage, this voltage V. That means across this node N1 and this node N2, the voltage is always this V, total voltage. However, the currents through individual resistors will vary. Like I1 is for R1, I2 current is for R2, and I3 current is for R3. Okay, now the total current of this branch right here, which is I, will be summing up all the branch currents. That means those branch currents are additive, which means I is equals to I1 plus I2 plus I3. You can think this one as a, this is a ocean and these are three rivers. So the ocean current is basically divided into three rivers. So summing up all the waters in three rivers should give up to the total water that is flowing in this ocean, just like an analogy. Okay, or you can think of something bigger. This is a bigger pipe, so this is a bigger pipe. Okay, now from this pipe, so this pipe has a specific current flow this way. Okay, now from this pipe, if you make three small pipes, okay, so one is this one, another is this one, okay, and another is this one. So pipe 1, 2, 3. Okay, so this current, and this current. So total flow is this I, and individual flows are I1, I2 and I3. So summing of all these three currents will give to this main current. So this is the concept of like parallel resistors. Now the powers are always additive here as well. That means total power P is equals to P1 plus P2 P3. You can say PT. Okay, now conductances are additive. So I forgot to say one thing. So if R is resistance, so conductance we refer to as G, which is equals to opposite of the resistance. So this one is called conductance. Now, so think about the voltage V is equals to I1 R1, and we also know that V equals to I2 R2 and also equals to I3 R3, because we know that this voltage across node 1 and node 2 is V, and according to Ohm's law we know that V equals to, so this voltage is basically is a product of the current and resistance. Now we already know that the total current I is equals to I1 plus I2 plus I3. Okay, now what can we get from this one? We can get that I1 is equals to V over R1, I2 is equals to V over R2, also I3 is equals to V over R3. Okay, so now if we get here, so I equals to V over RT. Think about, there is a total resistance RT. Okay, now if the branch current right here is I, we can think of this circuit as a simplified circuit where only one branch current is flowing here, and instead of all the resistors, this is a total resistors right here. Okay, so V, this current is I. Okay, now instead of this circuit, we can think of a circuit like this. This resistor is basically coming from all these three resistors right here. Okay, now here I1 is equals to what? V1 over R1, I'm sorry, V over R1. Similarly, I2 is equals to V over R2 and I3 is equal to V over R3. Now cancelling V from both sides, we know that RT is to 1 by R1 plus 1 by R2 1 by R3. Okay, now this RT is basically total resistance, so RT is equal to equivalent total resistance. So you can either remember this expression to find out the RT. So what is basically RT? Equals to 1 over also you can remember this expression. So we can write down that conductance, so GT is equals to G1 plus G2 plus G3. This is in terms of conductance. That means conductance are additive right here. So actually we know that G is inverse of R. Okay, now for n number of resistors when if are connected in parallel, this expression 2 or expression 3 can be extended up to n. That means RT equals to 1 over 1 by R1 plus 1 by R2 plus 1 by R3 plus dot 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 plus 1 by Rn. Also we can write down the GT equals to G1 plus G2 plus dot 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 plus Gn. So in this way you know that how to calculate the total equivalent resistance from parallel circuit. Now let's try to find out the current divided rule. That means we will find out an expression of individual branch current. How we can do that? So we are interested to find out the current I1, right? So say I1 is equals to V over R1. That we know from Ohm's law, right? Because the total voltage across node 1 and node 2 is V. Similarly, I2 is equals to V over R2 and I3 is equals to V over R3. However, we are interested to find out the branch current in terms of total current I. So we already know that V is equals to I times R. Now if we think about this entire circuit, so this will be equals to I times RT, right? Now if we come back right here, I1 equals to, then replace this V with IRT, so I times RT over R1. In simplified form we can write down RT times over R1 times I is equals to I1. So this is coming from current divider rule. In similar way, if we are interested to find out the current I2, it will be RT over R2 times I. This one will be expression 2, and in this way you can find out I3 is equals to RT over R3 times I. So this is known as current divider rule. That means whenever the total current I is given here, you can find out the individual current. Now a generic expression of current divider rule. That means if n number of resistors are connected here, then how will you find out the equation for the current IN? It will be RT over RN times I. Where RT is equals to equivalent resistance of the circuit, RN is the branch resistance, I is equals to total current. Okay, so it's easy to remember in this way. Only change is right here and right here. Okay, that means for a particular branch, if you would like to find out the current for a particular branch, divide the total resistance with that particular branch resistance and multiply it with the total current. So this is the current divider rule. Easy to remember, right?
Now let's see some series parallel circuit. To solve this kind of problem, you have to identify which components are connected in series and which components are connected in parallel, and then attack it accordingly and then solve the circuit.
Now we have a circuit which is basically this one, terminal, and 12 volt is across this. So what is the value of unknown resistor R in this figure? If the voltage drop across 500 ohm is 2.4 volts, that means this voltage, okay, is known, V500. This voltage is known. So from our gained knowledge so far, we have to find out the value of unknown resistor R, and we have given that the value of voltage drop across this 500 ohm resistance is 2.5 volts. Now let's see what we know. Okay, so we just name this one is R1, this one is R2, this one is R3, this one is R. Okay, now so far with our knowledge we know that, say V500, we name it actually equals to I times R3, right? We know that this is 2.5 equals to I times R3 is equals to 500. So from here we can find out I equals to 2.5 over, so basically it is 5 times 10 to the power minus 3 ampere. Now we know this current right here, we name it I3. Okay, it will be easier for you to remember. Now the I3 current is flowing right here, so the same current is flowing through this 50 ohm resistor, right? Now we know that V2 can be calculated using I3 R2, 5 times 10 to the power minus 3 times 50, 0.25 volt. Okay, now we know what is the voltage drop across this. Say this is C and this is terminal D. So resistors R2 and R3, so R2 and R3 are connected in series between this C and D terminal, right? So the voltage, if this one becomes V2 and this becomes V3, will be additive. So the voltage across CD, VCD, will be equals to 0.25 plus 2.5 equals to 2.75 volts. Now think about this portion. So total voltage AB, VAB equals to 12 volts. Now the voltage across this CD, VCD equals to 2.75 volts. Now V across R is equals to basically how much? Same voltage, 2.75 volts. Now what is the value of voltage VR1? So that will be equals to 12 minus 2.75 volts, which is equals to 9.25 volts. Now you know the voltage across R1, so you know the current, this one I, say it's I1. So I1 equals to then 9.25 over 550, 0.0168. Now what is the current that is flowing right here? So we can easily find out IR equals to the total current I, this is I1 minus I3 equals to, so the total current, okay, we got this current here, so, and we got this current here, so 0.0118 ampere. Now we can find out what is the value of R equals to V R over I R equals to 2.75 over 0.0118 equals to 233 ohm. So this is our final answer.
Now let's try to solve this series parallel combination circuit.
Calculate the effective resistance of the following combination of resistances and the voltage drop across each resistance when a potential difference of 60 volts is applied between points A and B. Before solving this circuit, we have to understand what is the series and parallel combination. So this 3 ohm resistance right here and this 6 ohm resistance, these two are connected in parallel with each other because they have a common node here and another common node here. So this complete branch is again connected in series with this one. Okay, now this complete portion is now again connected in parallel with this one, and then this complete portion is now connected in series with this one. So you have to go step by step to solve this circuit. So what is the resistance between terminal A and C? So we term it RAC is equals to 3 ohm is in parallel with 6 ohm. So 3 times 6 over 3 plus 6 equals to 18 over 9, 2 ohm. We know RAC. Now what is RAD? So RAD is basically RAC. This is connected in series with 18 ohm, and this whole combination is parallel with 5 ohm. Okay, what we get, so RAC we know 2, so basically it will be 2 plus 18 is in parallel with 5, so 20 times 5 over 20 plus 5 equals to, so 100 over 25, 4 ohm. So we know RAD now. So what is the value of RAB? RAB. Now RAB basically RAD plus 8 ohm because they are connected in series. Think simply, this one is terminal A, terminal D, another resistor, and this is terminal B, so 8 ohm, something like that. So we can think of AD, this is RAD, as an equivalent resistance, okay, between terminal A and D. So these two are connected in series, so which makes it 4 plus 8 equals to 12 ohm. Now this is basically the total equivalent resistance of this circuit. Now we have to find out the voltage drop across each resistance when a potential difference of 60 volts is applied. Now think about this circuit. Now think that a 60 volt is applied here, 60 volt, so equivalent circuit, right? Now from terminal A to terminal B, we can see terminal A and B, this is 8 ohm here, and we have RAD. Now we can use like a back calculation, okay? So the back calculation is simple, something like that. We can use a voltage divider rule. So to find out the voltage across 8 ohm, we term it V8 equals to, voltage divider rule is the voltage across which we have to determine the voltage, then the total resistance RAD plus 8 times the voltage applied across those resistors, right? So 8 over RAD is equals to 4, so 4 plus 8 times 60, 40 volt. So 8 plus 4, 12, 5 times 8, 40 volts. Now we know this is 40 volts across this one. So if VAB is 60 volts and only VDB is 40 volts, we can use voltage divider rule, or like we can subtract from the main voltage this 40 volt to get the voltage across 8 and D. So as we are familiar with voltage divider rule, okay, we will go with that. So VAD is basically RAD over, so this will be equals to 4 over times 60, 20 volt. So you see, sum of these two basically equals to 60 volts. Now once we know the voltage across terminal A and B, we know that this 5 ohm resistance is connected. So this 5 ohm is connected across terminal A and D, right? So we can say that V5 is equals to this VAD. Equals to 20 volts. So this is another answer. Once we get the VAD, now this part we can simplify here in this way. So one resistance, this is RAC, and the resistance, this one is 18, and this is terminal D, this is C, this is terminal A, and voltage across A and D is 20 volts, right? So we can find out what is V18. V18 is equals to, using voltage divider rule, so 18 over RAC plus 18 times the total voltage is 20, which makes it 18 over, so RAC is 2 plus 18 times 20 equals to 18 volts. Now we already know another voltage, right? So if we know V18, we can subtract the total voltage, like 20 volts, to get the voltage across A and C. So VAC is equals to, we know the total voltage is 20 volts, we already know some voltage, that is 18 volts, so is equals to 2 volts. This VAC is basically this A and C applied across 3 ohm and 6 ohm, so equals to V3 equals to V6. Now we know all the voltages. VAC, so we know all the voltages. VAC is basically, so 2 volts, so 2 here, and then 18 here, so 18 plus 2 is 20. VAD is 20, we already know VAD is 20, and now we got, so this one is 20. Now we'll all know that this one is 40, so total makes it 60 volts. Thank you very much. Please subscribe my channel to watch more videos like this.